Alright, this video should be pretty short and cover just the last two periodic trends that we haven't looked at. We're not going to spend very much time on electron affinity. I just wanted to tell you what it was and the rough trends, but there are a lot of exceptions here. So an affinity for something is a liking for. So an electron affinity, what it's referring to is the energy change that goes with the addition of an electron to an atom. So ionization energy was the energy required to remove the electron. Electron affinity is not quite the opposite, but similar to the opposite. It's the energy difference when you add an electron instead. And so just generally on trends, as you go to the right on the periodic table and stay in the same period, so if we have the same energy level, remember that the thing that is changing as you go across is you have an increased ZF, or number of protons. So as we move across the periodic table, the elements are arranged so that in general they have an increasing electron affinity, an increasing liking for electrons. Now the weird thing about electron affinity is that they're generally, the first ones are generally a negative value. And so we say an increasingly negative value. What that means is something like -2, -4, -6, -8. Those numbers are actually getting smaller, but in science we use the negative in front of an energy change to represent the direction of the energy change. And so it's not actually a smaller quantity, it's a bigger quantity in a different direction. So generally electron affinity has an increasingly negative value as you move across the same energy level, but you increase the protons. And then as you go down the periodic table, remember that the elements are arranged so that we have an increased number of energy levels. So the valence electrons, where you would put a new electron if you were going to get one, or an atom would get one, the valence electrons are further and further away from the nucleus, so that nucleus has a smaller and smaller attraction for new electrons. So electron affinity generally has a lower negative value down a group. So it generally decreases negatively down the periodic table. So -8, -6, -4, -2 would be what it would do down the periodic table. So there are lots of irregularities that happen with this, so we're not going to spend much time. I just want to introduce what it was, and you would have to study that in much greater detail to be able to understand all the differences and all the different factors. Okay, but the last trend is one that we're going to use a lot starting in the next unit. Electronegativity. What you have to understand is what we're meaning by this. So electronegativity is the relative ability of a bonded atom to attract shared electrons. What that means is now for the first time we're going to compare two atoms to each other. So let's say we had an atom here and an atom here. Okay, the blue atom and the pink atom. And so what we're going to get into next unit is what happens when they want to start sharing electrons. So I'm going to draw in just a few electrons. Okay, and what happens if they were going to share? And so to be able to share, the atoms have to have their valence shells overlap. That's what would have to happen, is a sharing. But we're not going to get too detailed into that right now. What you have to understand in the definition is a relative ability means we're comparing the two versus each other. So when we're looking at this, we're looking at the blue atom's ability versus the pink atom's ability to attract these shared electrons, the ones that they would both claim credit for, that would be in between them. So the relative ability, so it's just a ranking. Okay, and then they have to be in a bonded atom, some kind of bonded, so there has to be at least two atoms here. And then to attract the shared electrons. So think of this as a tug-of-war. And you had to rank the two, and they're fighting over these electrons, and you have to give a ranking to each one. Okay, so in general, on the periodic table, if you look at it, if we were going to compare two things as we went across the same energy level, So the ones I've drawn do not have the same number of energy levels. But if they have the same number of energy levels, then the change in the protons is increasing as you go across the periodic table. So the ones that we have sorted and put over toward the right on the periodic table have more protons than the ones that we have put on the left side of the periodic table. What the protons do is attract the electrons. So as you go across the periodic table, the more protons generally causes an increased ability to attract shared electrons, the more protons you have. So in general, electronegativity increases across the period because you get more and more protons and you have the same number of energy levels, same number of valence shells, and so those protons attract it more strongly. As you go down a group, remember what happens again is that you increase the number of energy levels. And so the idea there is those protons that are attracting those shared electrons are further and further away. So the atoms that I drew in here are an example of this. So if you look at the blue atom versus the pink atom here, the nucleus of the blue atom is much closer to those shared electrons than the nucleus of the pink atom. And so in general, as you get more energy levels, it is your ability to attract shared electrons goes down because your nucleus is farther and farther away from those. So in general, electronegativity decreases down a group, okay, from top to bottom, because you have more and more energy levels and the nucleus is farther away from those shared electrons. So it is a ranking, and so there's a periodic table written here with the rankings of all these elements, and in no way would you ever have to memorize them, but there's a couple details on here that I wanted to point out to you. First and foremost, there are no rankings over here in the noble gases. And there's a reason for that. So noble gases have ionization energies, they have electron affinities, they have atomic radii, they fit into all of those. But if you remember the definition of electronegativity, it was the relative ability of a bonded atom. So it was a ranking. And so we do this all the time as humans, is we compete, we put in competitions people, we put wrestlers and basketball teams, academics, we put them against each other and we rank them. And we give them rankings based on their performance. However, if you imagine, if I asked you, okay, what is your PGA Tour ranking? So what is your ranking of list of all the golfers that play professionally? You would say, well, I don't have one, and that's because you don't golf professionally. So electronegativities are rankings of bonded atoms, and the noble gases don't bond naturally, so we don't give them rankings because they don't participate. And so the noble gases you generally won't find that have electronegativities. You will find that a couple of them, humans, have forced xenon and krypton to bond, and we've then given them rankings, but they naturally don't do that. Okay, so then otherwise, other than the noble gases not having rankings, fluorine has the highest electronegativity on this periodic table with the elements that we know. So back in Unit 5, we talked about oxidation numbers, and one of the rules was that fluorine has a -1 charge whenever it bonds with anyone, and it never loses. And oxygen has a -2 charge, and oxygen loses only to fluorine. And so then if you find oxygen as well, this is why those little rules existed, because of their electronegativities. So fluorine here is the highest electronegativity. No matter who it bonds against, we have found that it always has the higher ability to pull the electrons toward it. So it will always pull in the negative, okay, versus anybody else. And then oxygen, if you look at oxygen's electronegativity, it's second highest. Oxygen will always attract the electrons unless it's up against fluorine, and then it will lose to fluorine. Fluorine will drag the electrons toward it, leaving the oxygen positive. So that's where those things came from, those different rankings, those oxidation numbers. It's because of observations of what we've seen in nature, and we just look back and go, okay, who did we give the highest rankings to? Who battled who and won? Okay, and so in general then, if you look at the general trends from lithium to fluorine, as you go across the periodic table, the electronegativity increases. Okay, and then in general, as you go down the periodic table, so we'll go over to the halogens here. As you go down the periodic table, electronegativity decreases because those shared electrons are getting further and further from the nucleus. Okay, so those are generic trends. Remember, that's never an explanation of where they're at on the periodic table. We have placed them there because of their properties, not their properties are caused by their placement. Okay, the last little anomaly I wanted to show you was hydrogen. All year long we've talked about that hydrogen really doesn't belong over here. And we've placed it over here because it has some different properties. It has one valence electron, like lithium, sodium, potassium, rubidium, etc. And it generally makes a positive one charge. But then as far as its electronegativity, it attracts those electrons much more strongly than any one in these two families because it has very few energy levels. It has that one proton and it has the one electron that's very, very close to it. And so hydrogen's a little bit different, doesn't really fit in our trends. It really belongs in a family by itself. And so you have to remember that hydrogen's a little different. And so we have made up definitions of types of bonds based on the electronegativity differences. Okay, so I do want you to consider this all a tug of war. Okay, so if you had a tug of war, okay, between something that was very strong and then something that was very weak, and you asked them to pull on a rope. Okay, so think about an NFL lineman and then a toddler trying to play tug of war. Well, that's not really even a tug of war. What happens is the really, really, really strong one ends up with the complete rope themselves, and the toddler doesn't have one. And so that's not even a tug of war anymore. Nobody is still playing that game. What we call that in science is if one atom rips those electrons that they're fighting over completely away, we call this an ionic bond because the electrons are completely transferred. This atom over here would become a negative, an anion, and this atom over here would become a positive because it lost the electrons, a cation. And then there would be now an attraction between the two of them because opposites attract here. There would be a coulombic attraction between the positive and negative, but they're not sharing anything. So that's what we call an ionic bond. And that happens when one atom is a lot different than another atom. Okay, but what happens if the two things that are fighting over the electrons are exactly the same or very, very similar in their strength? So imagine a set of twins. Okay, if they're both pulling on those electrons, no side is going to win, and they're going to continually, that tug of war would last forever. Okay, or until someone else stronger came along and ripped the whole thing away from both of them. Okay, but that tug of war would last a long time, and you wouldn't see any kind of side winning. And so we have learned back earlier this year that when atoms share electrons, we call it a covalent bond. Okay, but now we're going to give it a different modifier that we learned a little bit earlier this year, but we didn't really understand it. We're going to give it a modifier and call it nonpolar. So what nonpolar is that there is no side that is different. There is no tip to this molecule or anything like that. There's no obvious positive and negative side. No side is winning. So a nonpolar covalent bond happens when neither side has an obvious advantage. And so a nonpolar covalent happens when electrons are relatively equally shared. And where we have defined this is that if their electronegativity difference is between 0 and 0.3. And it's important that you notice that it says the difference. So looking back at these rankings, if you put two atoms together where their differences were less than 0.3, or from 0 to 0.3, so let's say we put boron and phosphorus together. Let's say hypothetically put those two together, and you had them fight for electrons. Their electronegativity differences are so close that you wouldn't really see any side gaining any kind of advantage. Now you would see like, okay, phosphorus has a slight advantage, but it's too small to really have a big effect on the overall molecule. And so what we call this battle between the two, if they're sharing electrons, is we call that nonpolar. Okay, if that difference between them is between 0 and 0.3. So then what happens, the last category, is if one side is definitely stronger than the other, okay, but not so much so that they rip the electrons completely away. Just stronger so that the tug of war ends up being pulled more toward the side of the stronger atom. Okay, so this picture is not a good picture. So think about a tug of war where one side definitely has an advantage, but not so much that they win outright. So they're still fighting, but that weaker species is being dragged toward the stronger one. So what we call this, it's still called a covalent bond because they're still sharing, but we call it a polar covalent bond because there's going to be an obvious side that has the electrons more. So since the electrons are tipped more toward the stronger atom, they get dragged in more toward that. This guy comes up kind of negative. And this little symbol right here means partially. It's a Greek lowercase delta. Okay, but it means kind of negative. It hasn't won completely, but it's kind of negative. And then this guy right here ends up kind of positive. Now it's not an outright positive or negative, so they're still sharing those electrons. But that has a big effect because if other atoms and molecules come along that also have positives and negatives, there would be attractions between them. And that's a big deal if you're in biology at all, talking about what happens with water and hydrogen bonding. But for us right now, we're just looking at this individual bond. And a polar covalent happens when electrons are unequally shared. So one side definitely has an advantage. And what we've given this this label to is when the electronegativity difference is between 0.3 and 1.7. And so a big good example is for water. Water, we will learn how to draw this next unit. But water has oxygen fighting against hydrogen 2 times, or 2 different ways. But if you look at oxygen at its electronegativity, it's 3.5 versus hydrogen is a 2.1. So that's a difference of a 1.4. What that means in each one of these tug-of-wars is that oxygen is going to drag the electrons toward itself. And so what that causes is that oxygen is going to end up with a more negative portion, and the hydrogens are going to end up with more positive portions. Okay, and that's a big deal for how water behaves. But that's all we've described this as. So between 0 and 0.3, we call it nonpolar for the electronegativity difference. Polar we call between 0.3 and 1.7. And those are rough divisions of these things. And then if it's bigger than 1.7, we call it ionic because one side completely ripped things away. So the most classic ionic that we've used all year is sodium chloride. So if you find sodium and chlorine, that's a huge difference. And what we learned earlier this year is that sodium is going to lose that electron and become positive, and chlorine is going to gain that electron and become negative. Okay, and then they're going to stick together because there's a Coulombic attraction between the positive and the negative. But chlorine definitely won that. And so we see that based on their ability to attract shared electrons, their ability to rip those electrons away. Chlorine has the much higher ability. Okay, and so that's what we designate as different kinds of bonds. So this last slide here is just a recap of the periodic trends. Remember, the trends are never a reason. They're just an observation for us that kind of helps us realize how this thing is organized. So across the periodic table, the shielding stays constant, the atomic radius decreases, the ionization energy increases, and the electronegativity increases. Why this all happens, all these trends happen, is that the nuclear charge increases, which is the number of protons. Okay, down the periodic table, the nuclear charge does increase still, but the effect of that is overridden by the number of shielding electrons, or the number of valence shells, or the number of electron shells, sorry. There's only one valence shell. But that causes the atomic radius to increase, the ionic size to increase, if you were looking at that, the ionization energy, how hard it is to rip an electron away, to decrease, and the electronegativity to decrease. Okay, and that's all based on the number of energy levels. All right, so those are periodic trends.